All right. I hope everybody had a good lunch. Our next speaker is also going to be virtual, and it looks like he's there. Uh,
Hello.
so, yep. Hey, Carl. So, Dr. Carl Mallings is from Morgan State University and also the NASA Goddard Institute, Goddard Space Flight Center in the U.S. And he's an expert on sensors and satellites and all kinds of great things. And so he's kindly decided to join us virtually to give a quick overview of some satellite data and other options for air quality from satellites. So I think, Carl, you can probably just do a screen share and
Yeah,
control.
let me try that. And then if it doesn't work, I believe I put the slides in the shared drive.
We see
All right,
you.
so I
We see your slides now, and I think everything looks pretty good. So I think you're good to go.
okay. Yep, we'll try this, and then let me know if there's any problems.
Okay.
But yeah, thank you for that introduction, Dan, and thank you everyone for coming today to this part of the training. In this presentation, I'm going to try to give you a brief introduction to an overview of how satellite data can be used to support air quality applications. So the outline I'd like to go through is first kind of a general introduction, talking a little bit about why space agencies like NASA are involved with air quality, what role those agencies play, um, talking a little bit about sort of the general background of satellite data for air quality, the basic concepts. What does remote sensing mean? What are different orbits and how do they impact the kind of data we get from satellites, things like that. I'll talk a little bit more specifically in two sections about measurements of aerosols from space, some instruments and missions related to that, and also about measurements of trace gases impacting air quality from space, and then some of the data and data products and missions that are available to support that. I'll then go to kind of general applications where satellite data has been used, talking about the relationships and the ways of relating what satellites see to what's measured by ground-based observations, which was the topic of the training that you've been attending previously or up to now. I'll talk a little bit about modeling of air quality and the roles they play, the roles that models play, especially in making those connections between the satellite data and the ground-based data. And then I'll talk about different methods of combining all these different information sources together to get a better understanding of air quality. And finally, I'll finish off with just briefly introducing some data access visualization resources available from NASA, as well as sources for additional information and future training if you want to go more in depth into these topics on your own. So the general motivation for why we might care about satellite remote sensing, one of these is the fact that I'm sure has been brought up several times in the training up to now of the relative scarcity of ground-based air quality monitoring in many parts of the world. So I have a figure here that I put together a few years ago now, based on the publicly available information about how many monitors are deployed in different countries, and you can see that, especially if you consider that horizontal axis there showing the density of PM 2.5 monitors per million people of population on a regional basis, if that you see that that's in a logarithmic scale. So there's quite a bit of disparity there in terms of how much ground-based monitoring is actually available, even taking new technologies like low-cost sensors into account, which are increasing that availability. There's still quite a bit of discrepancy there, and that's a place where I hope to sort of show you in the next few um, minutes why satellites can help to resolve that. So this is sort of the general schematic of the kinds of information sources we might consider when thinking about air quality. So I mentioned just now the traditional reference type monitors as well as low-cost sensors. They're under ground-based measurements in the upper left. That's one category, and that's not something that a space agency like NASA is involved with, but instead NASA tries to contribute to all these other categories and make contributions there. So I'll talk briefly in the next couple of slides, just introducing what those are. Um, First and foremost, and this is going to be the topic for most of the rest of the talk, is satellite data. So agencies like NASA operate these fleets of Earth orbiting satellites, and many of these satellites either have a primary or a key secondary mission of observing the state of the Earth's atmosphere. And by doing so, they infer information which is relevant, which can be relevant for air quality. And throughout the course of this talk, I'm going to expand on that in more detail and talk about some of the key satellites and missions which I've highlighted here, which are most relevant for providing this information relevant for air quality. I showed briefly on the previous slide ground-based atmospheric observation. So what this basically means is instruments on the ground, but they're not measuring necessarily the conditions at the ground level. They're really looking up through the atmosphere to infer what's happening throughout the rest of the atmosphere above their location. So examples of that, which you may have heard of, the AeroNet network. You can see a map of that on the upper left, showing sites around the world that measure aerosols in the atmosphere. There's also the Pandora network for trace gases, a bit of a similar objective, but more focused on trace gases. And many times, or the main focus of many of these instruments is not necessarily for air quality, but at least from NASA's perspective, the main value that these instruments provide is they're basically doing a similar thing to what the satellite's doing, where the satellite's looking down through the atmosphere from above. These instruments are looking up through the atmosphere from below, and by intercomparing and basically by comparing the data that these two different instruments, the satellite or the ground-based instrument, might gather, we can calibrate or mutually verify the data that these are providing. So that's the main value of these types of instruments from the perspective of a space agency like NASA. There's also airborne campaigns. So this is something that NASA and many other agencies are involved with, where we take aircraft with instrumentation on board, both in situ measurement instrumentation, where the aircraft is measuring the composition of the atmosphere that's flying through, as well as remote sensing information. So a similar kind of instrument to what I'll talk about later, which might be installed on a satellite and may, in some cases, be prototypes for future satellite instruments, would be mounted to the aircraft and would be flown around to look below the aircraft. So these campaigns, of course, provide a lot of useful data in very focused areas. For example, there was the CPEX-CV, the convective process experiment from Cabo Verde. That was an experiment from 2022, looking, obviously, as the name suggests, in the vicinity of Cabo Verde, looking at convective processes. So gathering information relevant to that. So really, these provide us a lot of data which we can build a better understanding of these types of processes. But of course, there's a limited number of these aircraft. They're very expensive to set up and run an operation like this. So not necessarily useful for more routine assessments of air quality, which may be more of your focus. But just the idea that we're gathering a lot of concentrated data about the meteorology, the chemistry, the properties of aerosols and things like that, and putting that all together, bringing that together with models to really try to improve our basic understanding of the underlying chemistry and physics governing things like air quality. And then the last bit I'll talk about is models of the Earth system. So where I specifically sit within NASA is called the Global Modeling and Assimilation Office, or GMAO. And the purpose of the GMAO is to use computer models of the Earth system together with data assimilation techniques to enhance and support NASA's program of Earth observations. So the basic idea is to take the data collected by satellites, bring it into Earth system models using techniques like data assimilation, which I'll discuss a little bit more later, and using those now refined models of the Earth system to both do basic science as well as to provide relevant information for other NASA missions and for the general public. So that's a model being a mechanism whereby we can make sense of and put into context the different data we're collecting from all these different satellite missions and other missions, which I've just talked about. So that was a broad overview of sort of why NASA is working with air quality and the kinds of work that we do. So I'm going to focus now specifically on satellite data for air quality. And I'll start off with sort of the basic concept. So the basic principle by which most of these instruments are collecting information relevant for air quality is known as remote sensing, or typically passive remote sensing. And in passive remote sensing, the basic principle is radiation from the sun, so light is coming to the Earth, passing through the atmosphere, reflecting off the Earth's surface, passing back up through the atmosphere, and then being captured or detected by an instrument mounted aboard a satellite. And along this path, the light is interacting with and being affected by the various properties and the constituents within the atmosphere. And by assessing the impacts that those interactions have had on the light as it's passed through the atmosphere, we can infer something about the atmosphere from that. So we call that general process a retrieval, and we develop algorithms called retrieval algorithms to process the data and extract what we call geophysical quantities, basically physical properties of the Earth's system that we have inferred from this indirect data. Some common geophysical quantities relevant for air quality, which I'll be talking about today, are aerosol optical depth, which is basically a measurement of the total amount of light being blocked or otherwise prevented from passing through the atmosphere by aerosols or airborne particles in the atmosphere. Another thing, a term I'll be using a lot, is sort of a trace gas total column density. So that would be the average or the total amount of a given gaseous chemical in the atmospheric column that this light has been passing through. And we can use the spectrum of the light to infer something about those trace gases, which I'll talk about a little bit more later. So with this kind of a passive remote sensing approach, we typically don't get information about where along this light's path that those interactions might have occurred. So where, for example, vertically in the atmosphere, these chemicals might be concentrated. We just get information about the total amount that was present in the full column of the atmosphere that this light might have passed through. There's also, it's less common, and I'll spend less time discussing it, but I will mention there's also active remote sensing, in which the light that's being used for remote sensing is not coming from the sun. There's actually a instrument like a laser mounted on the satellite, which is emitting that light, and then that light is being reflected back and being detected by the same satellite. So in active remote sensing, we have a little bit more of an ability to, for example, determine where vertically in the atmosphere these interactions are taking place, because we can time, from sending out the laser pulse to receiving back the reflection, we can use that travel time to infer the distance. But there are also limitations to that. The laser can only aim at very specific points, for example. So we will only get information from, the location directly underneath the laser, whereas, as you'll see later, we get more of a broad area information from passive remote sensing. And for that reason, I think passive remote sensing has typically been the main focus of satellite instruments for air quality. So at a very high level, sort of what are the advantages of using satellite data for air quality applications? And I think the key ones which I want to highlight are, as I mentioned, the large area coverage from this passive remote sensing. So on the left, the upper left, you can see data collected from the TRPOMI instrument on the tropospheric column density of nitrogen dioxide in the atmosphere. And this is a compilation of all the data collected over the course of a day for Northern Africa. And you can see we're getting a fairly good coverage over this domain in terms of those blue to red color spectrum indicating the actual data. There are some limitations here. There are some gaps in the data due to clouds and the white. You can clearly see that. But on the whole, we're getting this wide area perspective. And you can clearly see, for example, where the hotspots are. So potentially major sources. You can see, not so clearly in this image, but you could sometimes see plumes and how those plumes are being transported and moved from one area to the other. So it's generally, that's one general advantage, is this wide area view you get with a single or maybe only a few passes of the satellite instrument. Another advantage is looking at changes over time. So many of these instruments have been operating for many years, in some cases decades, in a very consistent manner. And what this allows is for long-term tracking of these broad area trends. So on the upper right, I have some data from the NASA nitrogen dioxide trends website,